Okay, let's do this example here. 1,100 joules of energy is done by a force of 260 newtons and a distance of 12 meters. Find the angle between the force and the distance. So this question, we've got a certain amount of energy, but the energy is done at a force and a distance. So that tells us that that's going to be work. So this is actually work. This energy is actually looking at work that is being done because there's a force applied over a distance. So I've drawn out these two scenarios that this question could be talking about. It doesn't necessarily say whether our object is being pulled by, say, this could be a string, you could be pulling a crate, or it could be pushing. The question doesn't tell us, but it also doesn't matter. Whether it's pushing or pulling, it's going to be the same answer, same angle, the same amount of work being done. And that's just an important thing to note. Whether you're pushing or pulling, it's going to be the exact same. That being said, let's get started with this problem. And I'm going to be color coding things as I go so that it makes it easier for everyone to follow along. So first I want to look at our variables. The variables that we have and the variables we're interested to find. So first we have this 1,100 joules of energy. I'm not going to write that as energy because I'm actually going to write it as work because this is, again, force applied over distance. So it's going to be work. So work, that's our first variable, is equal to 1,100 joules. Now what's our next value? We have a force of 260 newtons. And in this diagram, I've shown it in blue, so I'm going to keep it in blue here. So we got a force equal to 260 newtons. And then next, we're going to have a distance of 12 meters. So that is the distance that the object is moved during which the work is calculated. So that distance, I'm going to call it delta D, is equal to, again, 12 meters. And then finally, our last variable, which is our unknown, is find the angle. So this angle here, which I've done in pink, that's our unknown. So I'm going to write that here. Theta is equal to question mark. It's our unknown. So that is our variables. That's our variables. Now let's look at what formula we're going to use. We actually have a formula that uses these four variables, and it's an important one to know. That's what I'm going to write out here, is that the work is equal to the force times the distance that force is applied across, or the distance that the object moves, that the force is being acted on, times cos theta. So just looking at this formula for a minute, if we have a block, it's on the ground, and our force, remember what I said holds true, whether your force is a tension, pulling it, or pushing it, it's going to be the exact same, result in the exact same movement. So for the purpose of this diagram, I'm just going to show it as a pulling force. And here we have the force being pulled, and we have a little angle there, but it's the theta is actually 0 degrees. So here, when theta is equal to 0 degrees, our cos theta is equal to cos 0, which is equal to 1. So if we are pulling in the same direction as the movement is occurring, our cos theta is equal to 1, so the work is just equal to F times delta D. And in the other case, if we have a force that is acting directly downwards, that's kind of like an angle theta equals 90 degrees. So we have a force acting at 90 degrees. And in that case, cos theta is equal to cos 90 is equal to 0. So that tells us that according to this formula, if one term is 0, that the work is 0. So that's just another thing that's kind of interesting to watch out for and to be aware of, is that you have these kind of two extremes for this formula. One where the force is in the exact same direction as the movement, and in that case your cos 0 is equal to 1, and in the other case it's perpendicular to the movement, and in that case cos 90 is 0, so there's no work being done by this force. Right, so that being said, I want to carry on with this problem. With our next step is to plug in our variables. So when we plug in our variables, I'm just going to take this equation down here and rewrite it. So W is equal to F delta D cos theta. And I'm going to plug in our variables into this equation. So our work, remember, is 1,100 joules. Now that's equal to 260 newtons multiplied by delta D. It's going to be our 12 meters times cos theta. And I'm going to keep the cos theta in pink, just so that it's clear to see how these variables here that we started with have been entered into this formula. So now I'm just going to multiply these two terms together. That gives us an answer of 3,120 Newton meters. And one more thing, while I'm doing this, I'm going to change the units in these joules. Change it to Newton, the base units of joules is kilogram, meter squared per second squared. And again, this is all multiplied by our cos theta. All right, so now what we're trying to do here is isolate the equation for theta. So the next step in doing that is going to be to bring this term to the other side of the equation. And since it's a multiplication here, it's going to be a division on the other side of the equation. So I'm going to write that out. And it's going to get a little bit tricky with all these messy units here. But I'll try to keep them as organized as I can. And remember, we're bringing this term up here down, be a division, and Newton meters is the units on that. And I'll clean up these units in the next step. Times cos equals cos theta. Okay, so plugging this into our calculator, we get an answer of 0.35256. And now these units, let's see what we can do with them. Well, I'm gonna write these out. just as they are, over seconds squared. I'm going to write this meters. Now what's the units, the base units of newtons? Well, it's kilogram. Let me write it out here. It's kilogram meters per second squared. So the way I'm going to write that is kilogram meters. And then if we did a per second squared, it'd be the same thing as writing second squared on the top, because dividing is the same as multiplying by the reciprocal. So writing kilogram meters per second squared on the bottom here would be the same as bringing this per second squared to the top. So that's all I've done here, and I'm going to just color code these so you can also see what the significance of every term is. So the newtons, that's our kilogram meter per second squared. This original kind of messy units we have, that's a joule. That's written here. And then our last one, that 1 meter, is that 1 meter. So I hope you can see how this is all working. And what's going to be interesting now is that all these units cancel out. So second squared, meters squared cancels out with the 2 meters, and kilograms with the kilograms. And all that is equal to cos theta. So we're just about done here. To isolate for theta, we have to do the cos inverse. So theta is equal to the inverse cos of 0.3265. So theta is equal to, and plug this in your calculator. Remember to put your calculator in degrees. 69.35577 degrees. And this just keeps on going. So in our final answer, we're going to round it off to 2 significant digits, because that is how many significant digits we were given in the question. So it's equal to 69 degrees. All right, and that is the solution to this problem. So that angle that we just found there was 69. Theta is equal to 69 degrees. And again, that's the same for all of these. 69 degrees, 69 degrees, 69 degrees. So I hope this solution was easy to follow along, and that is the end of this video.